Okay there, Rusty Cowboy people. I'm going to conclude the Rust thread, at least temporarily, at a good sort of stopping point because I do have everything building. Now, if you're just joining this particular thread, there's at the math forum something called the Quadrays papers. Now, whether this is still here or not by the time you see this video, who knows, right? But there were a lot of collaborators on this project when it originally got started. And there's still evidence of that if you look at the Wikipedia page. If I search on QuadPod in my blogs in Control Room, I get this kind of meditative caltrop. It's actually shooting rockets. It shows you that you can go in any direction with these four. You don't need six, right? And four seems to be a minimum. We talk about a box, a minimum box. It's like with XYZ, three walls don't close the lid, so the box is implied. It's kind of the eighth of an octahedron when you have the three basis vectors as the edges of a box, right? But you always end up with the box of some shape. And you could say the sphere is what's morphing into these different shapes. So I wanted to have a coordinate system to go along with these. So let's see, where does this take me? I wanted to have a coordinate system that went along with me. Notice I've branded it Quaker geometry a little bit. I think the opening QU makes it fun. So that's kind of the thing I'm working on, right? And you don't have to rotate, i.e., negate, to get to any point. There's this thing with XYZ where you need your negative vectors to get everywhere, right? You can't just do it with only the positives. And that's okay, you know, why wouldn't additive inverses be included in the vector set? They all have their own additive inverse for sure, don't they? But if there is thrust in only one direction, there is some kind of asymmetry going on, such as with this. You see where 4 would be more like the minimum number of thrusters you'd need to get anywhere in space. So 4D, that kind of talk, is a topic here. But of late, a topic here has been the Rust computer language. And now that you've seen the two coordinate systems, like the one I assume you're pretty familiar with, is just XYZ. So this would be what we call a struct, and all it saves is three floating point numbers. And I'm being really simple kindergarten Rust here. I'm not using any generic type. I'm pinning it down to floating point 64-bit. Like, why can't I just use integers or maybe smaller floating points? You know, these questions. And could I write Rust that accommodated different number types? And I'm going to say yes, but I'm not doing that here. What I wanted to show you though was this idea of a trait where we sort of bolt this on to both types of ray. Like the ray is actually the interface. It's the dashboard to ray. The ray dashboard has adding, negating, subtracting, multiplying. You can multiply a vector by a scalar, a ray by a scalar, and that stretches it or it shrinks it. If you multiply by -1, that would flip it 180 degrees. So we do have that idea there, right, of negation. Then we have the implementation of that dashboard for the IVM vector, which is what I'm calling the one that takes four positive number coordinates, one of which at least is 0, right? So that's how we normalize. So what I've put into this particular new method for this particular structure is normalization. In other words, I have a step here where I find the minimum of the four coordinates and subtract it from all of them. And we're assuming already well, this is a good place to start in any case. I won't go into all the details, but to have that right there in the initialization and then to use that when necessary, when I'm creating and returning new things. For example, when I subtract, I just do straight across subtraction, but then I feed it all to new to get the new Q ray, or what I'm calling a IVM vector or vivim, right? And then I have the XYZ implementation for the just plain old XYZ vector operations. So I go back through the same methods over and over again, the ones that defined in the ray trait. So ray says, hey, if you're going to be a ray, if we're going to call you a ray, you got to know how to make a new one with this associated function, and then you got to know how to add two rays, negate a ray, negate meaning make it the negative of. You need to know how to subtract one array from another, and you need to know how to do scalar multiplication. We need all that, okay? And we need it for anything that calls itself array. And in this case, we have two candidates, the XYZ and the IVM rays. Now, what I don't have implemented yet, and I would consider the next step, is some functions to convert back and forth between the two. Okay? Once you count the normalized form of the IVM ray as the canonical form, then there is only one unique way to represent any given point in space. Understood that 1111 and 2222 are both names for the origin, 0000. So if you break the rule of normalization, it's like the equivalence class, however, can always be identified. Lowest terms you could say, like with fractions. 2/4 is really not simplified, 1/2 is what we want to say. So with quadrays, it's the same thing. There's a lowest terms normalized quadray that's unique for every point. Okay, so that's a Rust implementation, which they then test. And just to show that it's working, let's do a run task and pick to run this particular thing. And the output to the terminal is not that special, but that's okay. It's not giving us any errors here. It's just doing the job. Okay, thanks for listening, and we'll talk to you next time.